Welcome to the Generative AI Futures brought to you by ByteGoose AI, and welcome back to the deep dive. So we dug into your source stack, all those dense papers on things like NF4 quantization, grouped query attention, and this newer stuff like group relative policy optimization.
Yeah, some really cutting-edge material there.
Definitely. And our mission today really is to cut through that dense academic language and give you the core engineering principles behind how today's best large language models are actually built. We're moving past just, what they do.
Exactly. We're going deep into the how. How are they engineered for speed, for accessibility, and for complex reasoning? We're looking at the foundational shifts from attention tweaks to really sophisticated RL techniques.
Right. Not just the surface level, but the actual engineering trade-offs, the efficiency hacks, the alignment strategies.
Precisely. It's less about brute force now and more about, well, ingenuity, memory tricks saving researchers thousands, advanced RL teaching judgment.
Yeah.
It's fascinating stuff.
Okay, so let's start right at the foundation, the absolute core, the transformer architecture, and this constant battle to make its attention mechanism faster and leaner. So the transformer, it all hinges on self-attention, right? That mechanism letting the model weigh the relevance of every single token against every other token.
That's the one. It's the magic, but it's also, computationally speaking, the beast.
Beast.
Because every time it processes input, it generates this massive attention matrix, A. And the size of that matrix, it scales quadratically with the sequence length.
Meaning double the input tokens.
Quadruples the attention compute time. Roughly speaking, it becomes a serious bottleneck fast.
And you mentioned a conceptual issue, too, something about symmetry.
Yeah, exactly. The basic dot product attention tends to entangle similarity with the actual content. So the score between token A and token B is often the same as between B and A.
Like hammer is relevant to tool, and tool is equally relevant back to hammer.
Right. But sometimes you need asymmetry. Think about a specific term like ads versus the general tool. Ads should point strongly to tool, but tool maybe points weakly back to ads because it's just one specific example. Naive attention can lose that.
Okay, I see. And transformers process in parallel, so they lose word order.
Inherently, yes, which is obviously critical for meaning. Dog bites man versus man bites dog. Totally different.
So that's where positional information comes in.
Absolutely. You have to tell the model where each token is. The old way was adding fixed sinusoidal vectors or maybe learned position parameters.
But just adding fixed vectors feels a bit tacked on, doesn't it? Like you're injecting an external assumption. Do the sources mention newer ways like RoPE, rotary positional embeddings?
Ah, good question. Yes, RoPE, used in models like Llama, is much more elegant. Instead of adding position externally, it rotates the query and key vectors based on their position.
Rotates them.
Yeah. The clever part is the final attention score then depends only on the relative distance between tokens, not their absolute positions. It handles long sequences better because language often cares more about relative placement, the word before this one versus the word at position 57.
Okay, that makes sense. A much more integrated approach. All right, so we've got attention and position. But then these bottles got huge, billions of parameters. And the bottleneck shifted during inference, right, to KV cache.
Exactly, the key value cache. When the model's generating text token by token, it needs to store the keys and values for all the previous tokens to maintain context.
Yeah.
And that cache gets enormous, especially with long context.
Which led to multi-query attention, MQA.
MQA was a huge step for efficiency.
Yeah.
Standard multi-head attention, MHA, gives every query head its own key and value head. Lots of heads, lots of KV pairs, massive cache.
Okay.
MQA just said, wait, what if we share? What if we have only one key head and one value head shared across all the query heads?
That sounds drastic. Saves a ton of memory, I bet. But doesn't it hurt performance? Losing all that distinct KV information.
It can, yeah. There can be a quality hit sometimes. You lose some expressive power. And that's exactly where grouped query attention GQA comes in. It's a really smart compromise.
How does GQA work then?
It's a generalization. Instead of just one shared KV head, like MQA, or one per query head, like MHA, GQA divides the query heads into, say, TIA-draw groups. And each group shares a single KV head pair.
Ah, okay. So if you have 32 query heads, maybe you group them into like 4 groups of 8.
Exactly. So now you only have 4 KV heads instead of 32, like MHA, or 1 like MQA. It shrinks the cache significantly compared to MHA, but keeps more representational power than MQA.
So it's like a dial. GQA is MQA, max speed, maybe less quality. G number of heads is MHA, max quality, slower.
Precisely. GQA lets you tune that trade-off. Find a sweet spot, maybe G4 or G8, where you get quality almost identical to MHA, but speeds much closer to MQA. It's become pretty standard now.
And if you have an old MHA model, you don't need to retrain fully to get GQA benefits.
Nope. The conversion is neat. You take the KV heads that are now in the same group in your GQA structure, and you just average their weights. Mean
What's
pooling.
our average?
Yep. It preserves the core learned information while dramatically shrinking the footprint. Works surprisingly well.
Okay, GQA helps with inference speed. But what about training, or more specifically, fine-tuning? That used to need massive GPU clusters. Then QLoRa arrived.
QLoRa was, and still is, revolutionary for accessibility. Suddenly, fine-tuning a, say, 65 billion parameter model became possible on a single 48 GB GPU. That was unthinkable before.
And it supposedly matches 16-bit performance. How?
Three key innovations working together. The first is the data type itself.
Right, the 4-bit normal float, NF4.
Exactly. NF4 isn't just any 4-bit number. It's designed to be information theoretically optimal for weights that follow a normal distribution bell curve shape, which is very common in neural nets.
So those 4 bits pack way more useful information about the original 16-bit weight than a standard 4-bit integer would. Better precision and fewer bits. Okay, clever data type. What's the second innovation? Double quantization. Sounds complicated.
It's actually a simple but really effective memory-saving trick. When you quantize the main weights, you need to store some metadata, these quantization constants, usually as 32-bit floats.
Right.
Double quantization, or DQ, just says, let's quantize those constants too, usually down to 8-bit. It seems small, but it adds up.
The source mentioned saving like 0.37 bits per parameter. Doesn't sound like much.
But multiply 0.37 bits by 65 billion parameters, that's roughly 3 gigabytes of extra memory saved just by shrinking the metadata. On a tight 48 GB budget, 3 GB is huge. It can be the difference between running and crashing.
Wow, okay. That makes sense. And the third piece, paged optimizers.
That tackles memory spikes during training. Especially with adapter methods like LoRa, you get these sudden peaks in memory usage when gradients are calculated. Paged optimizers use NVIDIA's unified memory feature to automatically shuffle data between the GPU's fast VRAM and the slower but much larger main system RAM, CPU memory.
So it acts like a safety valve, prevents crashes from temporary overflows.
Exactly. It keeps the training stable even when memory usage fluctuates wildly. Put NF4, DQ, and paged optimizers together with the basic LoRa approach where you only update a tiny fraction, maybe 0.1% of the parameters.
And suddenly fine-tuning giant models is democratized.
Totally, and it highlighted something crucial. Data quality often beats quantity for fine-tuning. QLoRa fine-tuning on a small, clean dataset like OSST with only 9,000 examples actually outperformed tuning on much larger, messier datasets. The quality of the instructions matters hugely.
Okay, so efficiency makes models runnable. But alignment makes them usable, right? Helpful, harmless, following instructions. RLHF reinforcement learning from human feedback was the big breakthrough there. Hashtag tag 2.1, the RLHF alignment pipeline.
RLHF is really a multi-stage process. It starts with just teaching the model the basics of following instructions.
Phase 1, supervised fine-tuning, SFT.
Correct. Take your base pre-trained model, fine-tune it on high-quality examples of prompt in, good answer out, written by humans. This gives you your starting point, the base policy model. It learns the format of helpfulness.
Then you need to teach it judgment.
Phase 2.
Phase 2, reward modeling. This is the labor-intensive part. You generate pairs of answers to the same prompt and have humans choose which one is better. H is for winning, ace for losing.
Humans just voting.
Essentially, yes. Thousands and thousands of times. This preference data is used to train a separate model, the reward model. Its only job is to predict which response a human would prefer to output a score, reflecting helpfulness, harmlessness, whatever criteria you defined.
Okay, so you have a model that can judge. Now, Phase 3 uses that judge. Phase 3, policy optimization using RL. Now, you take your SFT model and fine-tune it further. But instead of supervised labels, the reward comes from the reward model. If the policy generates an output that the reward model scores highly, it gets positive reinforcement. The goal is to maximize this expected reward, pushing the policy towards generating answers humans would prefer. Hashtag 2.2 PPO and the stability challenge.
And the original RL algorithm used for this, especially by OpenAI, was PPO, Proximal Policy Optimization. Why PPO? What's special about it?
PPO is all about stability. Basic RL algorithms can be really unstable. A single update based on a weirdly high reward for one specific input could completely derail the policy, make it forget everything else.
Catastrophic forgetting.
Or just wild oscillations. PPO tries to prevent that using its core idea. the clipped surrogate objective.
Okay, break that down. What's being clipped?
It looks at how much the new policy wants to change compared to the old policy for a given action. It calculates the probability ratio. If that ratio gets too big, meaning the new policy is drastically different, PPO just clips it. It ignores how much bigger it got beyond a certain threshold. Typically, the ratio is clipped between, say, 0.8 and 1.2.
So if the model does something amazing and the reward signal pushes the ratio to 5, PPO just treats it as 1.2.
Exactly. It dampens the update, prevents one lucky shot from making the policy go haywire. It prioritizes making steady, incremental progress over potentially large but risky jumps.
But there's a trade-off there, surely, if you clip too much.
You get stability, but maybe you learn too slowly. You might never reach the optimal policy because you're too cautious. That clipping range, usually set around 0.2, meaning 1 plus minus 0.2, is a hyperparameter you have to tune carefully. Too tight, you underfit. Too loose, you lose stability.
Finding that Goldilocks zone.
Pretty much. BPO aims for safe learning speed. But this is key. It still requires training that separate reward model and another component called a value or critic model, which also takes resources.
Okay, so PPO is stable but complex. That complexity, especially the critic model, led to efforts to simplify things, right? Like GRPO group relative policy optimization.
Yes, GRPO is a really neat simplification, especially targeted at improving reasoning abilities efficiently. Its main advantage: it gets rid of the separate value model, the critic.
No critic. How does it estimate how good an action was then? Doesn't RL need that baseline?
It does, but GRPO estimates it differently. Instead of a whole separate model predicting state value, it looks at a group of outputs generated for the same input prompt within a single batch.
A group.
Yeah, you sample maybe 4 or 8 different responses to the same question. GRPO calculates the reward for each response in the group, finds the average reward for that group, and then calculates the advantage of each individual response relative to that group average.
Ah, so the baseline is just the local average within the batch.
Exactly. It's a much cheaper way to get a stable baseline for the RL update. Saves a lot of computation and memory compared to training and running a separate critic network alongside the policy.
Makes sense. A big efficiency win.
Did the research on GRPO show anything else interesting?
It did. Consistently, across different models like Llama and Quinn, they saw this clear S-shaped learning curve when training for reasoning tasks.
S-shaped meaning?
3 phases. First, a slow start, maybe the first 10% of training. Then a phase of really rapid improvement where most of the gains happen. And finally, a plateau where more training gives diminishing returns.
Okay, and the practical takeaway from that?
Don't overtrain. They found that performance pretty much maxed out after about 40% of a full training epoch. Pushing beyond that point burned a lot of compute for almost no extra gain in reasoning ability. It suggests you can stop GRPO training much earlier than you might think, saving significant resources.
Interesting. So efficiency isn't just the algorithm, it's knowing when to stop training it.
Precisely. And they also noted that model scale, like going from 3B to 8B parameters, generally had a bigger impact than the specific differences between the Llama and Quinn architectures, at least for the reasoning tasks they tested. If the reward model is the expensive part of RLHF, getting rid of it entirely seems like the next logical step. That's where direct preference optimization, DPO, comes in.
DPO is very elegant mathematically. It essentially found a way to translate the RLHF objective, which normally requires maximizing rewards from an explicit reward model, into a simple classification loss that can be optimized directly on the human preference pairs.
So no reward model needed at all.
Correct. You train the policy directly on the which is better data. It dramatically simplifies the whole alignment pipeline. No phase 2 reward modeling, no complex RL in phase 3, just a straightforward fine-tuning process using the preference data.
That's a huge simplification.
Yep.
But human preferences aren't monolithic, right? People disagree. Does DPO handle that diversity?
DPO itself mainly simplifies the mechanism. Dealing with the diversity of preferences is where other methods are emerging, like Nash learning from human feedback, LLHF.
Nash learning, like the Nash equilibrium in game theory.
Exactly that concept. Instead of finding one policy that maximizes an average reward, LLHF tries to find a policy that represents a stable point considering the distribution of human preferences. It aims for solutions that might better satisfy different groups or clusters of preferences simultaneously.
Trying to find a consensus, or at least a stable compromise, rather than just an average preference.
Kinda, yeah.
Yeah.
It's tackling the complexity head-on. And there are others too. Offset DPO, ODPO, adds a margin to DPO, trying to capture how much better they always is than lie dollars, not just that it is better.
Prioritizing the big wins.
Right. And Kahneman-Tversky optimization, KTO, tries to get rid of pairwise comparisons altogether, just learning from labels like good output or bad output. The field is moving incredibly fast, trying different angles to make alignment simpler, more robust, or more nuanced.
Okay, we've aligned the model's behavior, but raw reasoning power is also crucial. How do we get models to think more effectively? Chain of thought prompting seems key here. Hashtag 3.1, boosting reasoning with COT and self-consistency.
Chain of thought. Chemistry is beautifully simple. Instead of just asking for the answer, you prompt the model to show its work, to output the intermediate reasoning steps.
Like in school math problems, show your work.
Exactly. I start with 10 apples. I eat 3, so 10 3 equals 7. I buy 5 more, so 7 plus 5 equals 12. The answer is 12. Forcing those steps makes the model less likely to jump to a wrong conclusion.
So COT is about structuring the input prompt. What about improving the output? That's self-consistency.
Right. Self-consistency, SE, takes COT a step further. Instead of just generating one chain of thought, you use sampling during decoding to generate multiple diverse reasoning paths for the same problem.
Ask it to solve the problem, say, 5 different ways.
Pretty much. You might get slightly different steps, maybe different intermediate calculations. Then you look at the final answers from all these different paths.
And just pick the most common one.
Basically, yeah. You marginalize out the reasoning paths, ignore the steps, and just do a majority vote on the final answers. If 3 paths lead to 12 and 2 lead to 11, you go with 12.
Does that simple majority vote actually work well?
Surprisingly well. The research showed it performs about as well as more complex weighting schemes. And the impact on accuracy for arithmetic and common sense reasoning tasks is huge. We're talking gains of like 9% to over 20% absolute accuracy on big models like LLM-as-a or GPT-3.
Wow. So even if the model's single best guess is wrong, asking it multiple times and taking the consensus often gets you the right answer.
It taps into the model's underlying knowledge more robustly. The knowledge is often there, even if the first attempt fails. Hashtag 3.2, the mechanism of in-context learning, ICO.
All right, let's shift to another fascinating capability. In-context learning, ICO. The model learning a new task just from examples in the prompt, no weight updates.
It's incredibly powerful for quick adaptation. Give it a few examples of, say, sentiment classification, and it can often classify new examples on the fly.
But it's notoriously finicky, right?
Extremely sensitive. The exact wording of the prompt template, which examples you choose to demonstrate the task, even the order you put them in it, can all drastically change the performance. It's powerful, but brittle.
Okay, assuming you get the prompt right, how does the model actually decide which answer is best during ICL? How does it score the options?
There are a few main ways. The simplest is the direct method. It just looks at the probability the model assigns to the potential answer tokens right at the very end of the sequence.
So the answer has to be the last thing.
Yeah, that's the limitation. It restricts how you can format your prompt. Fast but inflexible.
What if you need more flexibility?
Then you use perplexity, PPO. It calculates the perplexity, basically how surprised the model is over the entire sequence. Context, query, and the candidate answer.
So it looks at the whole thing.
Right. Doesn't matter where the answer is, much more flexible template design. The downside, it takes significantly more compute time because you're scoring the whole sequence for each potential answer.
Trade-off between flexibility and speed. Is there a third way?
Yes, the channel model. This one flips the probability around. Instead of P-answer query, it calculates P-query answer. It asks, how likely is it that I would see this input query if this was the correct answer?
That sounds counterintuitive. Why do that?
It can sometimes perform better, especially if your training data for the underlying task was imbalanced. It forces the model to consider the generation of the input itself. Again, it's computationally more expensive, though.
Evaluating these complex reasoning outputs or just general helpfulness is hard. Human evaluation is slow, expensive.
Yeah, it doesn't scale, which is why using LLMs themselves as judges has become so common. LLM-as-a-Judge.
How does that work in practice? Are there standard benchmarks?
There are. You see things like AlpaCival, where they use a powerful model like GPT-4 to compare the output of a model being tested against a baseline model, like TextDaVinci 003, and calculate win rates. Or RewardBench, which is specifically for evaluating reward models using triplets of prompt, chosen answer, rejected answer.
Seems efficient. But using an AI to judge another AI feels like it could introduce its own problems, biases.
Oh, absolutely. It's a known issue and an active research area. 2 major biases keep popping up.
Okay, what are they?
First, model family bias. A judge model, say GPT-4, might subconsciously prefer outputs that look like they came from other GPT models, or models with similar architectures or training data. It might unfairly score outputs from, say, Llama or Mr. Lower.
That kind of unintended brand loyalty.
Sort of, yeah. The second is verbosity bias. Models often tend to rate longer, more detailed-sounding answers higher, even if the extra length doesn't actually add substance or accuracy.
More words equals better.
Sometimes that's how the judge model sees it. There can also be positional biases, like favoring the first response shown in a comparison. So while LLM-as-a-Judge is practical, you have to be really careful about interpreting the results and be aware these biases exist. People are constantly working on better, less biased automated metrics.
Let's circle back to pure inference speed one last time. We know attention scales quadratically and the KV cache balloons. How bad does it get?
It gets really bad, especially as we push context windows longer and longer. The sources highlighted that for contexts over, say, 80,000 tokens, the attention calculation itself can eat up 80% of the total time it takes to generate the next token.
80%.
Inky.
So optimizing attention is paramount for long context models.
Absolutely critical. It's the main performance wall right now. Hashtag Shack 4.2, turbo attention and quantization solutions.
So what are the cutting-edge solutions? The sources mentioned turbo attention.
Turbo attention is a technique aimed squarely at that 80% bottleneck. It's really a combination of two things, flash Q and SAS.
Okay, flash Q.
Flash Q is about running the attention mechanism using quantized values, lower precision numbers like 8-bit or 4-bit, but doing it in a way that minimizes the accuracy loss, optimized for speed.
And SAS?
SAS targets the softmax calculation within attention. Softmax normally involves operations that aren't super efficient on GPU tensor cores. SAS reworks that calculation to make it tensor core friendly, leveraging that specialized hardware for much faster computation. It speeds up a specific, often memory-bound part of the attention process.
So turbo attention hits both the computation and the memory aspects within attention itself. What about the KV cache memory usage specifically?
That's tackled by KV cache compression, usually quantizing the cache keys and values down to very low precision, like 2-bit or 4-bit. But how you quantize matters.
How so?
Well, they found that for some models, like Microsoft's Phi 3, the weight values have these large unusually large numbers. But these outliers are concentrated along the channel dimension.
Okay, and why does that matter for quantization?
Because if the outliers are channel-specific, then doing channel-wise group quantization works better than standard token-wise quantization. Grouping by channel allows the quantization process to handle those specific outlier channels more accurately, leading to less error and better model quality for the same level of compression. You have to tailor the quantization strategy to the model's specific characteristics.
Got it. Match the compression technique to the data structure. Hashtag 4.3. Mixture of experts, MOE architecture. Okay, final big topic, mixture of experts, MOE. This seems like the dominant paradigm now for building truly enormous models without costs exploding completely.
MOE is a fundamental shift. Instead of one giant, dense model where every input token has to be processed by every single parameter.
Which gets incredibly expensive as models grow.
Exactly. MOE uses conditional computation. It has a collection of smaller expert subnetworks and a gating network or router. For each input token, the router decides which are the most relevant experts, maybe the top 2 or top 4 out of, say, 64 available experts, and only activates those experts.
So a 1 trillion parameter MOE model might only use like 100 billion parameters for any single token.
Something like that, yes. The total parameter count is huge, giving it vast knowledge capacity. But the actual compute cost per token, the FLOPs, is much lower, tied only to the size of the experts that get activated, not the total size.
That's the efficiency breakthrough. How does the writer choose the experts? Just picks the best ones?
Usually, yes. Using a top K routing strategy, it calculates a score for each expert and sends the token to the K experts with the highest scores. But interestingly, adding a bit of randomness to this selection process actually helps.
Randomness? Wouldn't that hurt performance?
You'd think so, but it helps with load balancing. Without randomness, the router might learn to always send certain types of tokens to the same few experts, overloading them while other experts sit idle. A little randomness forces the model to utilize all the experts more evenly during training, leading to better overall performance and stability.
Makes sense. Spread the work around. And this routing doesn't have to happen just at the token level.
Correct. While token-level routing is classic, you can route at different granularities. Modality-level routing, like in Unimo, might have specific experts for image inputs and others for text inputs in a multimodal model.
Okay.
Or you could imagine task-level routing, where maybe one expert specializes in mathematical reasoning, another in code generation, another in creative writing, all within the same massive model. It allows for greater specialization and efficiency. #OutOutro.
Wow. Okay, that was definitely a deep dive. We've covered a huge amount of ground, from architectural tweaks like GQA making inference faster,
To quantization like QLARO with NF4 and DQ making fine-tuning accessible.
to the evolution of alignment, moving from PPO stability focus towards the efficiency of GRPO and the simplicity of DPO.
Right, and tackling preference diversity with things like LLHF.
And then boosting reasoning not just with scale, but with clever prompting like chain of thought combined with output aggregation like self-consistency.
Showing the model how to think and checking its work, essentially.
And finally, the massive shift with mixture of experts, enabling huge parameter counts, but keeping inference compute manageable through conditional computation and smart routing.
It really changes the scaling equation.
It feels like the bleeding edge isn't just about making models bigger anymore. It's about making them smarter, more efficient, better behaved through these really sophisticated engineering tricks, NF4, GQA, GRPO, MOE routing. So if the path forward is less brute force scaling and more architectural cleverness and targeted training, what's next? Are we going to see like swarms of smaller, hyper-specialized, maybe heavily quantized expert models that collectively outperform the current giants but use way fewer resources?
That's the billion-dollar question, isn't it? Maybe the future isn't one giant brain, but a highly efficient, coordinated team of specialists. We've seen the tools, the quantization, the efficient routing, the targeted alignment. Now it's about how they get put together next. Keep an eye on that interplay between scale, specialization, and sheer efficiency.